We are now recording. Let's get set up from the current slide. And we'll pick up there in just a moment. Let me go over just the activities happening today, tomorrow, and Wednesday morning, if that's appropriate, on Cougar Connection Week. This is Cougar Connection Week, and today on this campus, it's already underway, and you can't go to it because it would interfere with class. It's Constitution Day. They're going to have this tomorrow on the Birmingham campus from 12 to 1 in the Birmingham West campus, the library building, which is Building D, Delma Catlin Auditorium. If you can't find it, just ask anyone in the library. They'll point you there. You're right at it, but it's not really well marked. Okay, so Delma Catlin Auditorium. Tomorrow on the Birmingham West campus, D building. It's the library building. Constitution Day. Also happening today on Birmingham West Campus, what will be happening tomorrow here, is Get On Board Volunteer Fair. Okay? Now where it's happening over there, you can't get there in time for it anyway because it ends at 1. But on this campus tomorrow, it'll be from 8 to 1, and it's on the outside the library. Now, why they start at 8, I'm not sure, because classes don't start till 8:30, and there's just not that many students here at 8 o'clock. So, but that's when they're starting at 8 to 1. So if you come early, you can have plenty of opportunity, okay? And it's the location outside of the library, and my guess is, you know where the B building, the ground floor is, and the library, you come around that corner, there's a little courtyard there. And there's steps you go up to come in the main entrance of this building, the Student Services entrance, down there in that courtyard. And if they need to, they'll wrap around the library side of the A building, I'm sure. Some of the volunteer organization that probably will be present tomorrow are Big Brothers Big Sisters, Big Green Housing Authority, Bessemer Recreational Center, Faith Chapel, Girls Incorporated, Grace House, Hands On Birmingham, Humane Society, Metro Changers, Oaks on Parkwood, Operation Hope, Powership Network, and the Red Cross. Now, I think I've also heard that they had tried to get a blood drive going this week, but they couldn't. They were busy, so they're going to be here next week. So that'll be Cougar Connection Week for next week, going into next week as well. Now, there's also certain campus organizations you can become a part of, and they will have information tables and stuff out. Ambassadors, athletics, fine arts, honors college, PBL, which is Phi Beta Lambda, mostly a business type organization, but anyone can join. Scholars Bowl, Student Government Association, speech and debate, student support services, and science, technology, engineering, math, the STEM program. And also the math team, the prime examples, and you are prime candidates for that because you are the senior most math students we got here. So if you can participate on that, that's Fridays from 9:30 to 10:30. They meet on the Birmingham West campus in the science building, which is C Hall, room 100. Please go. Give it a shot. I think you'll find this lots of fun, and you'll learn math like crazy, and without even trying. You know, it just don't show up. All right, so that's tomorrow. Wednesday, I'll announce this Wednesday when we're in class for both of those. Birmingham and Bessemer, because those are both later in the afternoon. All right, any questions on anything we've covered so far? Okay, I was hoping more people might show up. They're not here yet, so let's just proceed. We were on page 831. This is chapter 12, vector valued functions. Did both of you get a copy of the test? Okay. All right. Vector valued functions. 12.2 is differentiation and integration of vector valued functions. and we were getting ready to do example 4, which is on the board right here. So R is 1 over Ti minus J plus log T K. U as a function of T, vector function of T, T squared I minus 2TJ plus K. And it says find each of these derivatives. Okay. Now, you got either one of two ways to do this. Okay. We can either use the properties of the derivative from the previous page, and it was the last slide, to do this, or you could actually do the dot product and then take its derivative. I really don't care. I don't know that one's any easier than the other. Which do you want to do? Take the dot product first. I like that idea. It just seems like to me. So this is the same. Let me get my pen set up. Okay. This is the same as d by dt of the dot product of those two. Well, how do we do the dot product? You do the i's times themselves, and what's that? T, okay? And then it's going to be a plus, because you do the coefficients of j times themselves, and what's that? Second? Plus 2t, perfect. And then the k's times themselves. This is the only sort of strange one, and it's not too strange. What's it? Log of t, plus the log of t. Okay? Well, let's simplify that a little bit. It's d by dt of 3t. T plus 2t is 3t plus log t. Okay? And what's that? Derivative of 3t plus log t is 3 plus 1 over t. You got it. Okay? Now, that to me is just about as easy as anything. If you looked at the number 4 from before, it's r dot u prime plus r prime dot u. Well, you have to take the derivative of each, and they're not hard, you know. Take the derivative of each of those. Let's just do it quickly. Here, r prime of t would be what? Derivative of 1 over t. Think of this as t to the minus 1. What's this derivative? Minus t to the minus 2. That would be I. What next? Yeah, there's no j because the derivative of minus 1 is 0. Okay? Plus second 1 over tk. Okay? Unless you do the u prime, and that would be 2ti minus 2j 0k, because the derivative of 1 is 0. Okay? Now, thinking back, number 4 is the r times the derivative of u. So r times the derivative of u, and these are dot products, by the way, that would be 2t over t. I'm going to, just to make it look a little simpler, I'm going to take these out of there because they sort of are messing up the picture. Now, let's see if we can do that. 1 over t times 2t would be 2 plus r times n prime, u prime, I can't read my own writing. The j's would be plus 2, and the k's would be 0. So this is 4, okay? That's r times u dot u prime plus u dot r prime, okay? Well, 1 over or t squared times a negative t to the minus 2 would just merely be a minus 1, okay? And the 0j, 0k we're missing something. I must have missed a product somewhere. Oh wait, no, yeah, I see. It's 0j, but the k we have. It's 1 over t. Okay, and then when you add those two together, 4 minus 1 is 3 plus 1 over t. I think I go with Justin in thinking let's do the dot product first rather than doing the rule, because there's just so many steps there and so many places that get mixed up. Now this one, on the other hand, we can do it either way. You tell me which way you want to do it. Take the cross product first, since we already calculated what u prime is, or do you want to do the rule on number 5 on the previous one, which we've already calculated all we knew, but then we need to do 2 cross products and add. What do you think? I just think 1 cross product. So u is, or r, t squared, okay, cross product. Back up, okay. What is cross product? How do you calculate it? Determinant of, and what's the top row? I, j, k, I, j, because I know I'm going to repeat that anyway, okay. And then the u is t squared minus 2t, 1, t squared minus 2t. Repeat the first two again. And u prime is 2t, that's your I part, minus 2, 0, 2t minus 2. All right, let's do our determinant. Okay, the first gives us 0 because you multiply by 0. Second gives us 2tj. Now you have to count, carry along these because cross products are vectors. What's this one? Minus 2t squared k. Now the up diagonals, I think I'll take off my other lines just because they get a little messy and hard to read. Okay? Up diagonal would be what? Plus, and it's a plus because it's minus this, and that's a minus, a minus, a minus. It's 4t squared k. That's ugly t. My pen wasn't writing, so I couldn't tell where I'd written and not. So let me see if I can make that look a little bit better. T squared k. All right. Next up diagonal is, second, plus 2i. Whoops. Okay. And the last up diagonal is a 0. So the cross product here, okay, we're doing d by dt of this vector, 2i plus 2tj plus 2t squared k. Right? And then what's the derivative of that? Two j plus 4t squared k. So, oh, 4t, not t squared. All right, sorry. And this is a vector because the derivative of the vector is a vector. And that's 2j plus 4tk. Got it. The other one was 3 plus 1 over t. All right. That's how we did it. Let's see how they did it. I think they used the rule, which is fine. There's nothing wrong with it. They first found what r prime and u prime were, which is good. Why they put u in such a big bold letter and r in such a small letter, I'm not sure, but that's okay. They changed, they changed everything. The i's are different, the k's are different, the t's are a little different, so I don't know. Whoever did the slide was not being very consistent. So the derivative d by dt of r dot u would be r dot u prime plus u dot r prime. Okay? So that's going to be their first step, I think. R of t times u prime of t dotted with u prime of t plus r prime dotted with u. And the r is that one. Well, they're just going on in. Oh, okay, they didn't show r, it's on the previous slide. But from your book, r was 1 over ti minus j plus log tk. They got it right. Dot that with 2ti minus 2j. Okay? And when you dot those two, that would be a 2, because you lose your unit vector symbols because it's a scalar. 2 plus 2 is 4. Okay? That was pretty easy. Plus, let me make sure they did that right. R prime is minus 1 over t squared I plus 1 over tk. They got that right. And the u was t squared I minus 2tj plus k. Got that right. So when you dot those two together, you minus 1 over t squared times t squared is minus 1. 0 on the j part and 1 over t on the k part. And you had a 4 from before, minus 1 would be 3 plus 1 over t. Pretty straightforward, and got the same answer we did. I think we had gone back and checked it and made sure that they were the same. Okay. Now, I think we go next to, oh yeah, here's where they did it. 2 plus 2 minus 1 plus 1 over t would be 3 plus 1 over t. Same thing we did. Oh, here's the B solution. They're going to do the cross product, derivative of the cross product. Well, by the rule, it's u of t cross u double prime of t plus u prime of t cross itself. Well, if you remember, u cross itself is, yeah, it's 0. Okay, because a dot product can dot itself, but a cross product can't. That's going to produce a 0. Okay, so it would just be u times u double prime. We had calculated what u prime was, but we didn't do u double prime. U double prime would be 2, just 2. 2i, okay, 2i. And there they set up their matrix like this. And it's pretty straightforward. Now, since the U double prime is just 2i, 0j, 0k. This last row down here is something in just zeros. The easy way to do this determinant, rather than doing the diagonals and stuff like this, is just take this one and multiply. Okay? Wipe out this row and this column. Okay? And then do j minus 2 plus 2tk. Determinant is the positive on the down, negative of the up. So that would be a plus 2tk. 2 times that would be 2 times 1 is 2j plus 4tk. And then plus 0, we already said, dot product, cross product by itself. The product of a vector by itself is 0. Okay? And they did it out in gory detail. Oh my goodness, why did they do that? But they could. It's perfectly fine. You get the same answer of 2j plus 4tk. All right, and hopefully that's what I said before. I don't remember now. Yeah, 2j plus 4tk. I said 2 times j plus 2t. Right. So, all right, that was example, what was it? Goodness, I've lost the page. Oh, yeah, that was example 4, previous page. All right, now we're going to do integration of vector value functions. Anyone want to hazard a guess how we're going to do this? Component by component, just like before. The following definition is a consequence of the definition of the derivative of the vector value function. The definition of the integration of the vector value function. If R of t is some f of ti plus g of tj, we're just going to do 2 space right now. F and g are continuous on some interval a to b, that's for I, going from a to b. Then the indefinite integral, or the antiderivative of r, which would be the integral antiderivative of r, be the antiderivative of component by component. F of t dt I plus the integral of g of t dt j. Okay? That's on the plane. If you're in space, add the third dimension out there. The definite integral over the interval from a to b would then be the integral from a to b of rt, which would be the integral from a to b of f of t dt I plus the integral from a to b of g of t dt j. And in 3 dimensions, just put the third dimension out there, the z, the k, and have that, then you just have a 3-dimensional integral and another 3-dimensional in both cases. Now, the one thing they haven't shown yet, and it's sort of understood, this is going to wind up with a plus c in it, and that's going to wind up with a plus c in it. Now, those c's don't have to be the same, because this is integral of f of t dt, that's integral of g of t dt. So you sort of have to do, and I like to do cx and cy and cj, or sometimes ck, or z, c sub z, or something like that to designate which one it goes with. But they're all just constants. And at the end, but they are also vectors, so they are part of the solution there, but just don't say plus c and then think all the c's are the same. They're not. They won't necessarily be the same. It could be, some of them, but it's not necessary. Okay, so there's your definition. The antiderivative of a vector value function is a family of vector value functions, all differing by some constant c. Okay? Again, I sort of cringe a little bit when I hear that. For instance, if r of t is a 3-dimensional vector value function, then for the indefinite integral of r of t dt, you obtain 3 constants of integration. Okay? where f prime of t is f of t, capital F prime of t is f of t, capital G prime of t is g of t, and capital H prime of t is little h of t. Antiderivatives, nothing's new there. Okay? Let me go back to this for a moment. All this is true, and they make it look like that's just going to add up to, oh, I'm sorry, okay. That's right. Notice that it's a constant vector c, where your c, what I was calling c sub x, is your I component of that, c sub y is the j component of that, and c sub z is the k component of that, but that's a vector c. Not a constant, it's a constant vector c, but it's a vector, not just a constant. So you don't just add these three up, you keep their dimensions with them. This is what I was saying before, but when I read that, I said, by a constant c. I thought, no, it's constant vector c. Okay. These three scalar constants produce one vector constant of integration, because you see the C1i, that's a component in the I direction, C2j is a component in the j direction, C3k is a component in the k direction, and that would give you a constant vector, C1i plus C2j plus C3k, which is some fixed value in x, y, and z. And that gives you this. The capital R vector, which is the antiderivative part of this, and there's the constant part. And when you take the derivative of R, capital R, you should get the little r, and we typically do. There you have a constant vector. Remember, that's a vector, not just a constant. Okay, find the indefinite integral of this. Okay, I think you'll find all that blah, blah, blah was a lot harder to read than it is to do. So what would this be? I think I'm going to write it right here. How would you begin? I can't hear you. Okay. My hearing is so bad I can't. Yeah, you do the antiderivative. So if it's helpful, do this. The integral of t dt I. You know, just pull out the function part, but leave your thing in, plus the integral of 3 dt j. Okay, this is two-dimensional planar figure. What's the integral of t dt? T squared over 2i. Okay, with one minor thing, we got to put our c's in there. Now, do you prefer C1, 2, and 3, or CX, Y, and Z, or CI, J, and K? Do you have a preference? Okay. The book does plus C1, and this will be times I plus, what's the antiderivative of 3 dt? Second, 3t plus C2 j. Okay? So this would be t squared over 2 plus 3t, this is I, plus 3tj okay, plus C1i plus C2j. All right. T squared over 2i plus 3tj and then we'll just call it plus C1I plus C2J. Just as good a way of doing it. This is a constant vector, and this is your variable vector. Okay. Example 5. And they just call this vector C. Okay. Which is fine. It's perfectly all right. So T squared over 2I plus 3TJ plus some constant vector C, which has components that you don't have to show. All right, let's see how they did it. Sorry, I tried to cram down my salad and my sandwich in the 20-25 minutes or so I had in my office, and I didn't drink enough, and now my throat is telling me, I'm so clogged up. I took a swig on the way by the water fountain, but that wasn't enough. All right, find this definite integral. Okay. Oh, wait, no, this is the one we just did. Okay. Integrating component by component, and all they did, rather than haul around the C1s and C2s, they just put vector C on the outside, which is probably the most efficient way to do it. Oh, and that was the answer. You just take the integral and put a constant vector outside. Now, that was example 5. Let's jump back and do example 6. That's where my mind was before, but I hadn't done 5 yet. Evaluate this integral. This is a definite integral. The integral from 0 to 1 of r of t dt, where that is equal to the integral from 0 to 1. My nose itches. We must be going to have company. Okay. Of the cube root of ti plus 1 over t plus 1 j plus e to the minus 1 k dt. All right, so there is your r of t, that big, long, hairy looking argument in there. That's your vector. Now, how would you begin with this baby? First thing I would do, write that radical in exponential notation. So much easier to take the antiderivative of exponential than a radical. So that would be t to the what? 1/3 power. There's your I component. Now, the jury's still out on this one. I frankly think it's easier to do this as t plus 1 to the minus 1j. Some people may argue just going to do the quotient rule. It's fine. If that rocks your boat, go for it. Okay, plus, and then this is fine just the way it is, e to the minus 1k. Second? Which is minus t? Oh, it's right. I can't read. That is a t there. All right. Thank you. I was going to say that's going to be a pretty easy thing to evaluate, but my eyes aren't good, and I thought that was a minus 1. Okay. Now, where would you go from here? Tell me. T to the what? 4/3, which is same as multiplying by 3/4, right? It's just easier. I mean, it is dividing by 4/3. That's the same as multiplying by, okay? and that's going to be I, plus, or in this case it's going to be minus, I can tell just looking at it, y, no I can't, or yes I can, no, I think it is going to be plus. What's the antiderivative of 1 of t plus 1 to the minus 1? Kind of botched this one. I think that one would have been better left as 1 over t plus 1. What's the antiderivative of that? Natural log. So that is no clearer. That would have been clearer, I think. Natural log of t plus 1. And I was putting absolute values on it because that's what you usually do when you do a natural log. But t is staying between 0 and 1, so this thing is always going to be positive. Okay? It can't go negative. So we don't need the absolute value bars. We can just put a regular parentheses there. Okay? All right. Plus, or in this case, I think this one is minus. What's the antiderivative of e to the minus t? Oh, I forgot my j here. Okay. Antiderivative of e to the minus t. Yes, negative. Okay, not t. You're taking the, oh, wait a minute. Oh, man. Okay. Right now, I want to say that, but let me pause for a minute. And if you took the derivative of this, you get 4/3 times 3/4 is 1 t to the 1/3. Got it. Take the derivative of this, you get 1 over that. Got it. Take the derivative of this, that'd be minus the e to the minus t times a minus 1. And that's exactly what we got here. So yes, that is the antiderivative of it. Minus e to the minus tk. Okay? And you evaluate this, between 0 and 1. All right, what does that give us? The one part is fairly easy to do. 3/4 of 1 to the 4/3 power is just 3/4 of 1. Okay, so that's 3/4 I. Okay. And when you plug in a 1 for the t in the middle term, it's just log of 2. Alright, Terrell decided he would grace us with his presence. So pleasant of him to do so. Okay. Increase the class size by 50%, so way to go. Okay. So the second part with 1 substituted in is log 2j. Okay? And the third part with 1 substituted in is what? Minus e to the minus 1k. Just plug it in. All right. Now we have to plug in the 0. And we're subtracting these off. Well, I can do the first one. 0 to the 4/3 power is still 0. So that's 0i. The next one, if you plug in 0 for t, you get log of 0 plus 1. And what's log of 1? 0, okay? So it's 0j. And then the third part is minus e to the minus 0, or e to the 0. What is e to the 0? Anything to the 0th power is? 1. So that would be plus k, just 1k. There is the only, so to clean that up a little bit, oh, I'm sorry, yeah, it is right. Because it's minus a minus, which is a plus. So that would be 3/4 I plus log 2j. I said j and wrote k. There's something wrong with my brain. Okay. J. All right. And then the k part, you would merely do minus e to the minus, or goodness gracious. Man. Okay. Minus, I'm going to write it as 1 over e. It's just easier to write than all these minuses there. Minus 1 over e plus 1 k, because you're just adding that to it. That's not quite right. If I'm putting it in the parentheses, then I better have a minus there. Okay. That's better. Because the minus e to the minus 1, that's a negative. The plus 1, that better be a minus times a minus. So I think that's the answer. Let's see what we've got. Just about the same thing. 3/4 I plus log 2j. And what they did was reverse those two and lose the minus sign, make it 1 times 1 minus 1 over e k, which is the same thing, okay? 1 minus 1 over e k. All right. Now, as with any, let's see if they have this. I don't think they have it. As with any real value function, you can narrow down the family of antiderivatives of the vector value function r prime down to a single mathematical antiderivative by imposing an initial condition on the vector value function of r. Okay, sort of some blah blah blahs. Okay, if I'm not mistaken, they don't have example 7 on there either, do they? No, they don't. I'm pretty sure. So I'm going to can this one. And before we do example 7, like I said, I didn't drink enough for lunch. I realize that now. Let me pause it just for a moment. Not doing well. All right. Let's do example 7. Find the antiderivative of this. Interesting. Find the antiderivative of r prime. Almost seems like a trick question, doesn't it? It's equal to cosine 2t I minus sine tj minus 2 sine tj. I usually like to put those in parentheses because it's just hard to read with the thing. Maybe they're bold, it's not as bad, but I don't write bold. Plus 1 over t squared k. 1 plus t squared k. Okay. Find the antiderivative of that that satisfies the initial condition R of 0 is equal to 3i minus 2j plus k. All right. Now, I can't believe it, but that's what they're asking. Okay? So, the antiderivative of a derivative is the function. Okay? So, r of t is equal to the antiderivative, that's the indefinite integral, of r prime of t dt, which would be okay, yeah, I guess they're right. They didn't give us what R of t was, that's what we're looking for. But when I saw antiderivative of a derivative, that seemed like we were coming back to the same thing we had, but we just don't know what we had to begin with. So that's why it's okay. So this will be the antiderivative of cosine 2t dt I, and to me then it's easier to do these like this, minus the antiderivative of, I'll put the 2 out here, sine t dt j, doesn't really matter where you put the bracket there, but plus, and this is the nasty one, the integral of 1 plus t squared, 1 over 1 plus t squared dt k. Running out of room there. Okay. First one, what's the antiderivative of cosine 2t? Second? Cosine 2t. Okay. The antiderivative of cosine 2t. Okay. Yes. With one little exception. The sine 2t is right over 2 because undo the chain rule. Okay. And that would be your I component. Okay. And we're going to have a plus c, but we'll do all those at the end. Okay? Minus 2, and what's the antiderivative of sine t? Negative, because the derivative of cosine is negative sine, so the antiderivative of sine is negative cosine. And that will make that a plus 2 cosine t j. Okay. Now this one. That is not a very pretty picture there. It's not a polynomial in any means stretch of the word. Does anyone remember what that one is? I was going to say before I glanced at what they did, I remembered, yeah, that's what it is. On something like that, I go to a table. That's where I would say go, and your integration tables are at the back of the book. And unfortunately, they number them strangely, okay? Because they're in the appendix, even though it's appendix B, they're numbered with A, 1, 2, 3, 4, 5. and this begins on A3 at the back of the book. Now, when I say back of the book, that's before your index, before your answers to the odd number problems. It's before all that. So it's not at the very back, but near it. Okay. So, what's the antiderivative of 1 over 1 plus t squared? Okay. Now, you almost need to know where to look. And you need to look in the inverse trigonometric function. So this is over number, nope, that's going the other way. So I guess we're going to have to do one. No, here we go. Nope. Okay. It's number 23, involving 1 over a squared plus or minus u squared. Well, we got 1 over 1 squared plus t squared. Okay. So your a is 1, your u is t, and that's number 23 is exactly that, and it's 1 over a, but a is 1, so it's arctangent of t plus c. So that's where I would go, and that's where you wind up going, plus, what did I say, arctangent of t. I don't like writing arc, I do inverse tangent of t. Okay. Now, it has a constant too. All those have constants, and this will be k, plus some constant, capital C, vector c. Okay, combining those things together. Okay, now what we're going to do is now plug in the 0 for the t. And what's sine of 0? Nope. Sine of 0 is 0. Remember, sine starts here and goes up and down. Sine of 0 is 0. Right? Cosine of 0 is 1. Okay? So this would be, when r is 0, r of 0 would be 0i. So I'm going to leave that blank. And then what is cosine of 0? So, yeah, 1. So that would be 2 times 1, 2j, plus, and inverse tangent of 0. Does anyone remember what that is? Tangent of 0 is 0, so the inverse tangent of 0 is 0. You're undoing it. So that's a 0k. So it's 2j plus the c. Okay? All right? And I'm just going to call it AI plus BJ plus CK. And this has to be equal to 3I minus 2J plus K. Okay? Now the 2J is taking care, oops, it's a minus. Okay? So if this thing on the left is equal to the thing on the right, 3 plus, A must be 3. Okay, because the i's have to be equal. 2 plus b has to equal minus 2. 2 plus b equal minus 2, so b is equal to minus 4. And c is equal to 1. Okay, so our constant vector there is 3i minus 4j plus k. Okay, So how we write our answers, I'm going to come up here where I drew my sine curve and use that spot there. So your R of t is equal to sine 2 where is that? Just right there it is. There it is. Okay. Sine 2t over 2 plus 3i plus 2 cosine t minus 4. Oh, is that right? Yeah. Minus 4j plus inverse tangent t plus 1. I believe it's, yeah, there it is. Plus 1. Okay. All right. I hope that's what they got. They put 1/2 sine 2t. That's fine. Plus 3i plus 2 cosine t minus 4j plus arctangent of t, or inverse tangent of t plus 1. Okay. Yeah. So there's their example 7 in gory detail. All right. That finishes 12-2. Homework exercises here. Do any of the odds 3 through 9. They're all at calcchat.com. 5's at calcview. Do any of the odds 11 through 17. They're all at calcchat.com. Excuse me. Do either 19 or 21 or both. They're both at calcchat. Do either 23 or 25 or both, and they're both at calcchat. 23's at calcview. Do any of the odds 27 to 33. They're all at calcchat. 27's at calcview. Do 35 is at calcchat and calcview. Do 37 is at calcchat. Do any of the odds 39 to 45. They're all at calcchat. 41's at calcview. Do any of the odds 47 to 51. They're all at calcchat. 47's at calcview. Do any of the odds 53 to 57, they're all at calcchat. 53's at calcview. And then there's an exploring concepts at 59. You can look at calcchat. I don't recall if it's there or not, but you can look. There's some proofs that if you're interested in doing any of those 61 to 67, and they should all be at calcchat. There's a particle motion problem, perpendicular vector. I'd say do any of those applied problems 69, either 69 or 71, or both. They're both should be at calcchat. And then true false do either 73 or 75. They should both be at calcchat. All right. Are there any more at the bottom? Yeah. So let's move on to 12-3. Let's see. Here we go. All right. 12-3. Now a little more applied problems. In fact, one of these looked very similar to one of the problems you had at the end of 12-2. You could wait and do them here, but I think you could do them either order. Okay, from current slide. We're looking at vector valued functions as before. Okay. This time we're looking at velocity and acceleration. Two very practical, applied type physics problems for vector valued functions. Describe the velocity and acceleration associated with a vector valued function and use a vector valued function to analyze projectile motion. One's going one way, one's kind of going the other way. As an object moves along a curve in a plane, okay, we're going to stay in a plane first. The coordinates x and y of the center of mass are each functions of the time t. Now, they can be functions. The curve doesn't have to be pass a vertical line test because your variable here is t, not x and y. Okay, x and y are dependent variables. T is the independent variable. So rather than using the letters f and g to represent those two functions, it's convenient to write x as x of t and y as y of t. That's very physics oriented. You know, a lot of mathematicians sort of frown on calling the variable a function too. You know, it's either a variable or a function, not both, but really, they really are. Okay? So the position vector r of t takes the form of r of t is equal to x of ti plus y of tj. The position on the x-axis is a function of time times I plus the position of the y variable as a function of time j. Okay. To find the velocity and acceleration vectors at a given time t, consider a point q at some little increment of time past t. Okay? Now, this doesn't look like a little increment, but it kind of is. Okay? If there's a p at some time t, and you're over here at time t plus delta t, where this is a pretty long delta t, or it looks that way, or it's going awfully fast one, that you're way over there at some incremental time later, then your consider a point that is approaching the point P. So now we're going to have it getting closer and closer. In other words, your delta T is going to get smaller and smaller. So it started off being here, then it'd be there, then there, and there. And each one of these delta R functions is doing like that until when the delta T approaches 0, which is a rather bizarre way of expressing it there, this is approaching the tangent line. Okay? Velocity vector at time t. And you're staying on the curve C. The curve C is, of course, this. So R of t is x of ti y plus y of tj. And that's your approach there. As t approaches 0, the delta R divided by delta t is approaching the velocity vector, which is the tangent vector, where delta t is going to 0. Instantaneous velocity vector. Okay. As t approaches 0, the direction of the vector pq, denoted by delta r, approaches the direction of the motion at time t, because you're getting closer and closer to the actual direction of the motion on there at that specific time, instantaneous motion. So the delta r is r of t plus delta t minus r of t. And when you divide by delta t, you get this form, delta r divided by delta t. This would be, and that is a vector there. It may not look the same as that one. I don't know why they changed fonts on it, but they did. R of t plus delta t minus r of t, so you change that too, over delta t. You just divided both of those by delta t. And then the limit as that delta t approaches 0 of that would be this. And what is that limit? That's your first derivative of r. When that limit exists, it's defined as the velocity vector or the tangent vector to the curve at point P. So your velocity vector is your tangent vector at that point P. Note that this is the same limit used to define r prime. That's exactly what it said. That was your r prime, or your derivative of r. So the direction of r prime gives the direction of motion at that time t. Okay. Moreover, the magnitude of that vector r prime of t is the magnitude of x prime of ti plus y prime of tj, which would be just the square root of x prime squared plus y prime squared. So it gives the speed of the object at time t, which is just your components of velocity vector squared, take the square root. Some of those take the square root. So, similar to how R prime of t is used to find velocity. You can use R double prime of t to find acceleration. Notice they're all vector quantities. Velocity is a vector quantity. Acceleration is a vector quantity if your displacement vector is a vector quantity. Definitions for velocity and acceleration of x and y are twice differentiable functions. Have to be to do acceleration of t. And R is a vector value function given by R of t is equal to x of t I plus y of tj using the same convention we did a little bit earlier. Sometimes skipping well. Then the velocity vector, acceleration vector, and the speed at time t are as follows. V of t is R prime of t, which is x prime of t I plus y prime of tj. The acceleration vector is this derivative of that. R double prime of R is R prime of the velocity vector, or R double prime of your displacement vector, which is x double prime of I plus y double prime j. And your speed vector, going back to this one, is the magnitude of your velocity, magnitude of the velocity vector, which is the square root of x prime squared plus y prime squared. Pretty much, I hope, just as you would expect, or at least hope it to be. Okay, and it is. Now, so let's think. Motion along a space curve. Now we're not on the plane anymore, but the definitions are similar. Now your R of t has three dimensions, x, y, and z in the k direction. And you have the following. The velocity vectors R prime, which is x prime of ti plus y prime of tj plus z prime of tk, just like you would expect. Acceleration vector is the first derivative of the velocity vector, which is the second derivative of your displacement vector, which is x double prime of ti plus y double prime of tj plus z double prime of tk, and the speed is going back to the velocity vector, and it would be the square root of x prime squared plus y prime squared plus z prime squared. That's your speed vector as a function of time. Okay. So nothing too new there, I hope. So let's do example example 1. Find first, A, the velocity vector, then the speed, then the acceleration vector for the particle that moves along the plane curve C, described this way. R of t is equal to, let me get my pen set up again, 2 sine t over 2i plus 2 cosine t over 2j. That's your position vector. And we want the velocity vector. So how do you define the velocity vector? It's take a derivative, R prime of t, and that would be what? Help me. Cosine of what? T over 2. And it's also a vector. I left off my vector symbol, but this will be I plus, or is it plus? Derivative of cosine is? Negative sine. And that would be 2 times 1/2, so you lose that, minus sine of t over 2j. So there is your velocity vector. They didn't say at any particular time, so there's your velocity vector. Cosine t over 2i minus sine t over 2j. All right, let's do the speed, which is the magnitude of that velocity vector, which would be what? Cosine squared t over 2. Now the t over 2 doesn't change. You're only squaring the cosine function. plus sine squared of t over 2. I can't write. Why is that in the way? Okay. Now what does that equal? What is cosine squared t over 2 plus sine squared t over 2? Think Pythagorean identity. Any ideas? 1. And square root of 1 is 1. So we don't need the square root sign anymore. This one just happens to be the speed is 1. Okay? Now let's do the acceleration vector. This is the A part, the B part, now the C part. And you go back to the velocity vector, and your acceleration vector as a function of time is your first derivative of the velocity vector as a function of time, which is the second derivative of your displacement vector as a function of time. And what would that be? Help me, help me. Here's your r prime right there. Let's take the derivative of it. What do we get? Anybody? Derivative of cosine. What sign? Negative, but not just that. 1/2 sine of t over 2. Now why the 1/2 out in front? Chain rule. Derivative of cosine of t over 2 is sine t over 2. But then you take the derivative of t over 2, which is 1/2. The derivative of cosine is minus sine, so the minus is there. The derivative of this is 1/2. So minus 1/2 t over 2. Next. Minus 1/2 cosine t over 2. And I'll have to put that. Oh man. I got so much to do this afternoon, I feel like I don't have any energy at all. Something messy, I don't know. All right, that should be what we're looking for. Let's see what they get as answers. Oh, they're going to show us in a minute anyway. So just taking a look, and sure enough, that's what I see. Okay, so let me clear my chicken scratch. And what we do first, velocity vector is first derivative of the position vector, which is cosine t over 2 I minus sine t over 2j. I believe it, excuse me, exactly like we had it. All right, so your r prime of t, the magnitude of that, would be the square root of cosine squared t over 2 plus sine squared t over 2. Well, that's just a Pythagorean identity if I've ever seen one. Sine squared plus cosine squared is equal to 1. No matter what you have after it, u, v, x, y, t over 2, 17 over 3, whatever you have there is going to be 1. Okay? At any time, it's 1. Constant velocity, but varying angles. And the c is going to be the first derivative of the velocity vector, which is second derivative of your position vector, which would then be a minus 1/2 sine t over 2 I plus well, that's what the answer is. It's 1/2 minus 1/2 sine t over 2i minus 1/2 cosine t over 2j. Okay. That's all we have to do on that. Now, let's go back and consider what we were just describing there. For that position vector, basically, if you kind of ignore the 2's and the halves in there, which just, they're just there, okay? What you have is something moving in circular motion. So sine is increasing from, when t is going from 0 on up, sine is increasing, cosine is decreasing, j is decreasing, and you've got the position vector like this. The x initially is 0, and the y is initially at 1. So you're starting up here and going around that way, I'm pretty sure. Okay. So that circular motion, the velocity vector, think about this, okay, go back up here. Sine starts at 0 on I and 1 on j, okay, and then goes like this, okay. Your velocity vector is starting at 1 on I and minus then basically 0 on j. So seems like that's backward. Now I just can't figure out why it's backwards. But the point being, no matter which way it's heading, by the time you get to the acceleration vector, your first vector, the displacement vector, is like this. Your acceleration vector is in exactly the opposite direction. Okay? That's a minus 1/2 j. So it's not the same magnitude, but in exactly the opposite direction. So anytime you have circular motion, your acceleration vector is always toward the center of the circle. Always toward the center of the circle. That's the pure circular motion. They're not exactly opposite each other. That's a fourfold difference in quantity, but the directions are exactly opposite each other. Okay. So that's what they were pointing out in their figure. I had hoped to see the figure, but they didn't. They moved right to projectile motion. Well, they didn't either. They're skipping examples 2, 3, and 4. So let's see if we can get 2 done. Let's go back and try to do example 2 here. Sketch the path of an object, oh, I love these, moving along a plane curve given by r of t is equal to t squared minus 4 I plus tj. All right, it's a plane curve going in that direction. Okay, it says find the velocity and acceleration vectors when t is equal to 0 and 2. We'll come back and do that in a minute. It says first sketch the graph of this. Well, this is what we call x of t, right? And this is what we call y of t, right? The x and y coordinates. Well, y of t is equal to t. That's the, on the y scale, that's the identity function. Okay? So in other words, your y is t. Well, if the y is t, then the x is t squared minus 4. Well, t squared minus 4, I'm sorry, y squared minus 4, because t was y squared minus 4, x is equal to y squared minus 4. That's, if it was the other way around, y is equal to x squared minus 4, you would have a parabola like this, right? So this is y is equal to t squared minus 4, so it's a parabola like that, opening on the y-axis, okay? Symmetric about the y-axis. So that's what the sketch looks like, and somehow I bet they don't show, oh no, of course they don't, because they're not even doing this problem. You have them in the book if you want to take a look at them. There they are, okay? So, that's your sketch, basically a sleeping parabola. But, remember this, now it's the full parabola. It's not just half of a sleeping parabola, it's the entire sleeping parabola, the one on horizontal, done horizontally. And you don't start yelling, wait, that's not a function. No, it's a function of t, not of x. Y is a function of x, or x is a function of y. Both of them are functions of t. So you can have on your xy scale, xy graph, something that isn't y as a function of x, not at all. It's both of them are functions of t. So you can have that on a parametric equation like we have now, a plane curve. Okay. Now it says find the velocity and acceleration vectors when t is equal to 0 and 2. Let's first do the velocity vector. What is r prime of t? That is your velocity vector, by the way, v of t. And what would it be? Pretty easy, I thought. What's your velocity vector? Anybody? 2t I plus j. There it is. There is your velocity vector, v of t. Now your acceleration vector, which is the first derivative of your velocity vector, which is the second derivative of your position vector, would be what? 2i. And that's all, folks. No j. No, well, there weren't any k's. Okay. And that's it. That's all they're looking for in that example. Oh, wait, no. Find the velocity and acceleration vectors when t is equal to 0. So your velocity vector, v of 0, would be what? J. Okay? And your acceleration vector at 0 would be 2i. That doesn't change. Okay? Constant acceleration. Okay? How about velocity vector when t is equal to 2, is it? Yeah. T is equal to 2. That would be what? For I plus j, right? And your acceleration vector, that's supposed to be a 2 there, and for some reason I wrote a t. I guess 2 starts with t. I don't know. 2, and that would be what? It's just 2i again. It's a constant acceleration vector, okay? I think that's all they're asking for here. V of 0 is equal to 2i. Wait a minute. V of 0, oh yeah, there it is equal to j, got it. And a of 0 is equal to 2i, got it. V of 2 is equal to 4i plus j, got it. And a of 2 is 2i again, still, because that's constant. Okay, any questions on that? How are we doing time-wise? 2 minutes. I don't think we can get example 3 done in 2 minutes. So sorry that I had to take that short break in the middle, but I'm feeling better now than I was then. We'll start with example 3 next time. Let me give you some homework exercises in 12.3. I think you can do any of the odds 3 through 9. They're all at Calc Chat. 3 is at Calc View. I think you can do any of the odds 11 through 19. They're all at Calc Chat. 15 is at Calc View. And I think we stop there because we'll do it going the opposite direction next time. Okay. So that will be it for this time. Any questions? Okay. Whew, goodness. I drug through it, but I'm through.